In UCM, uniform circular motion, the motion is along the circumference of a circle with constant speed. It means that it has a constant magnitude of velocity, it has constant angular velocity. As the constant angular velocity, there is no change of angular velocity, therefore in UCM the angular acceleration is 0. Example of uniform circular motion: when a fan is rotating with constant speed, at that time it is said to be, all the particles in the fan are supposed to perform circular motion with a constant speed. It's a uniform circular motion. The tip of the hands of the watches, they perform uniform circular motion because they need the same time for every revolution. It has constant angular velocity, 0 angular acceleration, and the speed of revolution and the velocity, tangential velocity, has a constant magnitude. In circular motion, we know that the velocity of a particle in circular motion, the linear velocity of a particle in a circular motion, let it moves from A to B through a small angle delta theta. The linear motion is along the tangent. It is represented by vector V. This is the angular displacement. This is the linear velocity. If the particle is performing anti-clockwise revolution, this is anti-clockwise revolution, like this. The angular velocity is perpendicular to the plane of figure. It is along the axis of rotation, and as it is here anti-clockwise, it is directed outward. Therefore, this will be the angular velocity omega. The vector drawn from the center to the position is the radius vector, vector r. How all the three are? As I stated, all the three are perpendicular to each other. Now, this is what? The anti-clockwise revolution of a particle. For this anti-clockwise revolution of the particle, this is for this anti-clockwise revolution of the particle, this will be the center, and this is the radius vector. This is parallel to the axis of rotation, along which we got a angular velocity, and this is the tangential velocity. All the three are perpendicular to each other. In uniform circular motion, it has constant angular velocity, it has constant magnitude of linear velocity, but in non-uniform circular motion, the tangential velocity has increasing or decreasing magnitude. The magnitude of tangential velocity is not constant. As an example, whenever you switch on a button of a fan, the speed of revolution of fan increases. With increasing the speed, it will trace more angle at every instant of time, and therefore its angular velocity increases. This angular velocity increases. Its final angular velocity is more after some instant of time. The speed of revolution, this linear velocity also increases. With increase in angular velocity, it has angular acceleration in the direction of angular velocity. Thereafter, the fan attains a constant speed, then it will be an example of uniform circular motion. It will rotate and rotate and rotate for some time, or for the time as you wish. Thereafter, when you switch off the button, the speed of revolution of the fan goes on decreasing. With a decrease in the speed, it needs more time to trace the same angle as the time passes. Therefore, there is a decrease in angular velocity, and decrease in angular velocity is again change of angular velocity, which gives angular acceleration. But now the angular acceleration in this case is negative, and it will be in a downward direction. Omega and alpha are in the same direction if angular velocity increases. If angular velocity decreases, alpha is opposite to that of angular velocity. This is what non-uniform circular motion is. Only things that we have to remember here is that in non-uniform circular motion, angular velocity is not constant, either it increases or decreases. The magnitude of linear velocity, which is along the tangent, is also not constant, either it increases or decreases. Then what will be the acceleration in uniform circular motion? That we will see initially by doing some mathematics, by calculus method, and thereafter we will analyze that mathematical equation and we will find out how the accelerations are in non-uniform circular motion. For that, what we will do, again we will have a famous relation between the linear velocity and angular velocity. We know that linear velocity v is related to angular velocity by the formula vector v is equal to vector omega cross vector r. This is the relation, famous relation between the linear velocity, angular velocity, and the radius vector. As far as the plane of revolution is constant, as far as the plane of revolution, in this case I have drawn a figure, it is revolving like this one in a horizontal plane and the axis is vertical. As far as the circular motion is in a horizontal plane, the axis is vertical and axis is at a fixed position. As far as the plane of revolution is same, the axis is fixed. This is the one thing which is very important to be noted. And the angular velocity and angular acceleration are in the same direction. Here we will consider the plane of revolution is same, therefore axis of rotation is constant and the speed of revolution is increases gradually with equal change in equal time. Therefore, what we are doing here is, for constant angular acceleration we are doing some mathematics. Angular acceleration is supposed to be constant here. There is a change of angular velocity, but it has equal change of angular velocity in equal interval of time. For that we will do some mathematics. Here the linear tangential velocity is related to angular velocity and radius vector by a relation vector v is equal to vector omega cross vector r. Here with little mathematics by calculus method, the rate of change of the linear velocity dv by dt is equal to, the first variable is kept constant, the derivative of second dr by dt plus the derivative of first variable d omega by dt, the second variable is kept constant. Here omega I am saying variable. No doubt r is variable, no doubt. It's a radius vector, it has constant magnitude, but the direction of r, we know that the direction of r changes like this one. Omega is also changing only in magnitude, not changing direction. As far as the plane of revolution is constant, omega, this is omega, it will remain at the same position, but its magnitude is changing. With increasing omega, the alpha increases. Alpha is there and it's positive. With the decrease of omega, alpha is there and it is opposite to that of omega. But what is the increase, what is the decrease, that is same at every interval, therefore alpha is constant. Therefore alpha is constant, omega is changing, therefore omega is variable here. Here dv by dt is the acceleration. Rate of change of linear velocity is the linear acceleration. I will keep here omega into dr by dt with the rate of change of position, that is the linear velocity, plus rate of change of angular velocity. It's angular acceleration cross r. This is what I get. Acceleration is equal to omega cross v plus alpha cross r. Now, this acceleration I will write. Now, this equation is homogeneous, no doubt. It's an acceleration on one side, and on other side we got two terms. One is omega cross v, other is alpha cross r. Now, the sum of these two is acceleration. Therefore, obviously, this should be acceleration again. It is also acceleration, and these are the two components of acceleration. This is component of acceleration which is perpendicular to omega and v. Omega and v. All the three are perpendicular to each other. Perpendicular to omega and v is r. Therefore, this acceleration is along the radius. Therefore, it is radial acceleration, ar. Now, this is alpha and r. Alpha is perpendicular to the plane of revolution, r is in the plane. For alpha and r, v is perpendicular and v is along the tangent. Therefore, this is perpendicular to radius, means along the tangent. Perpendicular to tangent is radius, and perpendicular to radius is tangent. Therefore, this component of acceleration is radial acceleration, and this component of acceleration is tangential acceleration. We will see the component independently. We will see the components independently. I will first talk of the radial acceleration component. This radial acceleration component I got. This radial acceleration component vector ar is equal to, what is that? Vector omega cross vector v. It is magnitude of radial acceleration is equal to magnitude of omega, magnitude of v, sine of angle between them. Omega, all the three are perpendicular to each other. Therefore, angle between omega and v is sine 90. Therefore, the magnitude of radial acceleration is omega into v. If I keep v is equal to r omega, that is r omega square, that is v square by r. Therefore, the radial acceleration, the first component of acceleration in non-UCM is radial acceleration, and it is r omega square. As we know that this acceleration is to change the direction of velocity. Therefore, it is must for all. This radial acceleration is must for both what? UCM and non-UCM. In UCM, AR is equal to V square by R has constant magnitude. Because V has constant value, the speed is constant. And in non-UCM, AR is equal to V square by R has a variable magnitude. Magnitude varies here. Magnitude of tangential velocity changes, magnitude of angular velocity changes. Therefore, in non-UCM, radial acceleration has variable magnitude. This is one component that we got for radial acceleration. Now, the another component in non-UCM is this one, this component. What this component is? The tangential component of acceleration. What tangential component of acceleration is? Vector alpha cross vector r. Now, magnitude of tangential acceleration, it is equal to, I should write it as alpha into r into sine of angle between these two. R and alpha are again perpendicular to each other. Therefore, it is r alpha. This tangential acceleration is r alpha. This tangential acceleration is because of change of magnitude of the tangential velocity and because of change of the magnitude of the angular velocity omega. And this tangential acceleration has a magnitude r alpha, and the resultant acceleration in non-UCM is under root of ar square plus at square, because ar and at both are perpendicular to each other. Resultant of these two is under root of ar square plus at square. Therefore, we will conclude in this case is that for UCM, the magnitude of velocity is constant, angular velocity has constant magnitude and constant direction as far as the plane of revolution is constant, angular acceleration is 0, tangential acceleration is 0. In non-uniform circular motion, the magnitude of linear velocity changes with time, the angular velocity changes with time, there is angular acceleration. The acceleration which keeps on changing the direction is the radial acceleration. Acceleration which keeps on changing the magnitude is the tangential acceleration. In UCM, only you have to change the direction of velocity, therefore it has only radial acceleration. In non-uniform circular, both magnitude and direction are changing, therefore it should have both radial acceleration to change the direction, tangential acceleration to change the magnitude. This is how acceleration is there in non-uniform circular motion. Thank you very much.